All right, so welcome back, and then we'll continue this last day of the workshop with the second talk of the day. And the speaker is Mark Vivray from Los Alamos National Lab. Please, the floor is yours.
Thank you. So welcome everyone. This is a joint work with my colleagues from Los Alamos, Siddhant Misra and Andrei Lokov, whom you know. I was going to talk about our long series of work on learning discrete graphical models and some new exciting results with neural assisted methods for learning discrete graphical models. So you heard the first talk of the day by Ankur, explaining a bit, actually while explaining what the graphical model were, especially Ising models. So I will try to take this example as a reference during the talk of a specific graphical model. So informal definition of graphical model learning, or if you want just probabilistic learning for those who are not familiar with, is like you just want to observe random variables that you see from experiments or from that you collect somewhere on the internet or wherever you want. And the goal is to learn a positive distribution, a probability distribution that represents the probability distribution of these samples, right? So this is a task that you would see or you want to do everywhere, which is an unsupervised learning task. So you have different numbers in this problem. The dimension of the problem is that you have a certain number of samples available that I will denote by n, a certain number of variables in this problem. So this is the random vector has a certain size, which is p. And of course, here we're talking about discrete graphical models. So the variables also have a certain alphabet q. In general, I will again refer to Ising models as little toy examples. So the size of q is 2, but you can take it as large as you want. So here you see the example of what this vector may be. So you have like these variables is indexed by I was from 1 to p, and this sigma can take this kind of generalized spin in a way, can take value from 1 to q. If it's like a classic Ising model spin, it will take values -1 and 1. So the problem of learning such a probability distribution in such a general class is that the worst case sample complexity will just scale the number of different probability distribution that you may create with this type of variables. So in this case, it just scales like exponentially with the dimension of p, right? This is why it's in general a hard problem, and you will not address a problem of learning a probability like this. So always what we try to do is to introduce some kind of priors. It can be on a parameterization on a certain class of model we want to learn, to reduce this complexity, computational and also observational, the number of samples you have to observe and how many computational steps you have to do to be able to learn this probability distribution. So by introducing priors in the parameterization on the class of model that we consider, we'll reduce this complexity to something that is tractable. So logarithmic in the size of p in this case. And learning graphical model is, or at least this is the way I view it, is a way to introduce some priors in the distribution or class of distribution you want to learn to make the problem tractable. So in a nutshell, just to kind of revisit in my notation, or maybe slightly different, what graphical models are, what kind of prior introduced by considering graphical model is that it's really, you want to consider probability distribution that have a certain dependency structure, and this dependency structure can be represented by a graph. So as you saw before, which is this Markov random field property, you consider a certain distribution where you have like independence relationship between the variables. For instance, you know that sigma1, one of the variables in your problem, conditional on sigma2 and 3, is independent of the rest. And if you know that this kind of relationship hold in the problem you want to learn, then graphical model language is adapted to represent such distribution. So in this case, this graph that you see represents is a graphical way to represent this independence property by saying like, oh, if you make a cut in this graph that separates sigma 2 and sigma 4 from the rest of the world, then sigma 2, sigma 4, and sigma 1 is independent from the rest of the world, conditional on neighbors. So it's kind of, if you cut and you condition the neighbors on this cut, then this variable in the center of the cut is kind of independent of the rest of the world. this is this Markov random field property that is captured by the graph. And well, the good thing is that if you have a positive distribution, you know that this Markov random field property also translates into a certain parameterization form through this Heimer-Circuit form theorems. So if you know that your probability distribution has this Markov random field property, you can factorize this distribution on the clique of the graph. So it kind of build a hierarchy of models easily by saying like, oh, if you only consider graphs which have like dependencies of 2 or 3 variables, you know it will be like pairwise or treewise, and the probability distribution can be parameterized with like an exponential of lower order polynomial. This is kind of the idea behind this. So for the Ising model, where you have like this only pairwise distribution, that means that if you just condition like one spin on its neighbor, you will be completely independent from the rest of the graph, and the neighbor are just considered as with pairwise edges, not hypergraphs. So this is kind of the idea behind graphical models. So in the talk, I'll first like draw a general framework for graphical model learning, like what is the problem exactly. In the second part, I'll just review the algorithm that we propose to learn the graphical models, and just briefly mention where it is situated with respect to previous works. And at the end, I will talk about this new method that is empirical to learn graphical models with neural nets. How to adapt actually this efficient algorithm with a neural network inside, and what kind of problem you may help solving with that. Okay, so let's focus on the framework for graphical model learning. So why is it non-trivial or difficult to learn a graphical model? I mean, if you're familiar with the question, this is not a surprise. But if you're not, what would you do if you have to learn a distribution? Is run maximum likelihood. And in this problem of graphical model learning, maximum likelihood is intractable. And this is because you have in the definition of graphical model it's always proportional. You always represent this as being proportional to a certain exponential family, and the proportionality factor, which is called the partition function, is in general hard to compute or intractable to compute. So there is no, if you want, readily method that you could apply. Like the standard tools don't necessarily work, because I mean you would be able to learn the distribution with a low number of samples or observations, but it's just you cannot run it computationally speaking. So what is graphical model learning, like more precisely defined? So you think that your probability distribution has a certain parametric form. You can parameterize it the way you want. It's part of an exponential family. So the probability distribution is proportional to an exponential, and inside you parameterize by a sum of different basis function times some parameters. And you're interested in learning these parameters. What you would observe are random draw that are IID from this distribution. So here everything is observable. There is no hidden layer whatsoever. So you believe that all the variables are observable. And your goal is to recover the parameters or a subset of these parameters up to a certain accuracy. So you'd like to estimate those parameters with an estimate theta hat, and you want this theta hat to be close to theta star in some null. So in the example of the Ising model is just considering like a model with pairwise interaction where you have like binary spins. So the G function, the basis functions are just product of these variables, or single variables, the bias or the field. And if you're interested to reconstruct the graph underlying those conditional independence relationship, then the type of norm you would like to reconstruct, in which you would like to reconstruct the parameter, is the L infinity norm. So you would like to make an error on the pairwise coupling, which is at as much as epsilon or epsilon over 2. Right. So that's the definition, if you want, of graphical model learning, of the framework. So of course, in such a problem, we have to know if it's possible to do this learning. So what are kind of the necessary or almost necessary condition to perform learning? And the necessary condition in a way is that the problem is well posed, it's not degenerate. So you should be able to infer a unique set of parameters from this model. So there are kind of two conditions that makes the problem well posed, and mostly one, but if you want two conditions. For those who are not familiar, there is one which is like you require that the probability or the conditional probabilities are bounded in a certain way. So you want that if you take one spin and condition on the rest, you want the probability to be still positive. So you want like each variable to have like a certain amount of variability if condition of its neighbors. It's a bit, if you think about Gaussian or normal distribution, the classical normal distribution, it's a bit like asking like the matrix is non-degenerate in a way. Like there is not like strong or perfect correlation between any two variables. And this measure of correlation, or perfect correlation between two variables is usually represented with using the log of the conditional probability distribution. So you want the conditional likelihood in a way not to be less than gamma for any assignment of the neighbors of a certain variable. That gives you a strength of how much variables are correlated in the worst case. So this translates, you can more or less, in the fact that the parameters that you have in your exponential family are involving one variable is bounded in L1 norm. So it's not a strict equivalence, right? But if you impose the prior and the L1 norm, then you will have like bounded conditional probability in this way. So this is something we can add in our example of the Ising model. If you want to learn a certain Ising model in a certain class, then we believe that we know something about this class. We know that the interaction strength between the variable is not exceeding a certain amount, which translate into L1 norm or L1 prior in the coefficients involving one variable. So we have this L1 prior inside the learning problem. That was condition number one. The second condition is that you would like the likelihood function. And here, since we're not looking at maximum likelihoods, but we want to do something with local information because maximum likelihood is intractable, we want the local conditional likelihood to be non-degenerate at the parameter of the distribution. So it's requiring that if you look at the likelihood and at a certain the right parameter, and you make a certain variation around it, this should not be degenerate. So you should not you should actually pay a price in likelihood. Likelihood should decrease. So if you look at the conditional Fisher information matrix, so it's the same as the Fisher information matrix. It's just with respect to the conditional distribution. What we ask is that this conditional Fisher information matrix, which is the Hessian of the conditional likelihood, is non-degenerate or is non-singular with respect to some perturbation. So we take a vector x, x transpose, we look at this matrix, product it, and we would like this to be greater than 0. And normally, if you were looking at a regular matrix, the norm that you would have on the right-hand side would be a 2 norm. This would tell you that there is no 0 eigenvalue. But in general, we ask this question for any norm, and the norm in which we're interested to reconstruct the parameter. Because sometimes it doesn't work for 2 norm necessarily, or sometimes it's asking too much for a 2 norm. You may want to be looking at an infinity norm instead. So you can view this as a sort of generalized eigenvalue in the problem, this rho variable, which tells you how much the problem is degenerate, or by which amount you can change the likelihood by adding a perturbation on theta star. So an Ising model, if I look at this conditional information matrix, it's looking almost similarly to a matrix with pairwise correlations inside. So you're asking that the matrix of pair correlations in your system is non-degenerate, and like with respect to a certain norm. If you're looking at the structure, it will be with respect to the infinity norm, and you hope that this constant in front or this generalized eigenvalue is actually not scaling with the dimension of the problem, because it will impact your computational complexity for the learning part. Okay, so those are the two main conditions for well-posedness of the problem. First one, the probabilities are kind of bounded away, no strong correlations. And the second is that the problem is really non-degenerate. The log likelihood is conditional log likelihood is non-degenerate. Okay, there is, well, something I can add for this Ising model non-degeneracy. There is like another way to represent this condition with respect to the Fission information matrix, which is kind of asking, there is no way you can create a magnetization that has a small variance. This is another way to see this eigenvalue, if you want like a more physics type of intuition. All right, so the algorithm for model learning. So you have seen in the talk by Ankur, he mentioned that the first algorithm that showed that it was actually possible to learn efficiently graphical models were presented by Guy Bressler, which was indeed a surprising result, because like doing inference in graphical model, especially in the regime of long-range correlation, can be hard, but it's always easy to learn a graphical model. So that was kind of the first results presented by Guy Bressler, a very efficient, greedy method, efficient in terms of computation to learn graphical models. And these methods were based on mutual information, like some inequalities that we're holding for conditional mutual information. And this way you could build a recurrent greedy method for learning the graphical model. The problem with these methods is that they were doubly exponential in this constant gamma, or this bound, this strong correlation between the variables that prevent them from being actually used in practice. So later there were like a new body of work looking at convex optimization based methods. Most notably the one by Adams and Raghu, and our work looking at different loss function to study graphical model learning. And these loss are in fact optimal both in the number of computational steps you need to do, and also in a number of samples, and you get rid of this double exponential problem. And you have like two families here, which are like conditional likelihood or conditional likelihood based loss, and the one I will describe now, which is this interaction screening loss, which is kind of different loss than conditional likelihood. Okay, so what is this interaction screening loss? So we have this probability distribution, we have our exponential family. This is our guess of what the probability distribution should be. And I will tell you to minimize this function. And what is this function? It's like take all the factors around one single node. So you on the probability distribution on the left, you have like all the possible nodes or variables involved. On the right, you just consider the factors that are attached to one single variable. You put a minus sign. You look at the empirical expectation of this loss, and you minimize with respect to the parameter, and you include also a constraint or a prior that the parameter in L1 num cannot exceed what you believe is the strong correlation bound. And that's it. This is your estimator. So first thing I can say about the estimator is that it does, like the other methods, all the methods I presented, it does like a reconstruction one neighborhood at a time. So you just look at reconstructing the neighborhood of one node. And if you do this for every single variable, every single node, then you'll be able to reconstruct the graph fully. The other part is that it's a convex loss function. So you have exponential, it's convex, you take convex combination of these exponential functions. So you end up with a convex function. And you can provably, optimize this loss with an efficient algorithm. In this case, you can use mirror descent type of algorithm. And you can provably minimize this function. So why this loss and why this function works? It's kind of magical, but if you look at in the infinite regime where the empirical expectation, you can replace it in a way by formally by the correct expectation, the real expectation on your problem, you can see that the gradient of this function is actually minimized or is equal to 0 when the thetas are equal to the true thetas. So it's kind of asymptotically consistent. Of course, it doesn't mean that for finite samples it will be efficient, but at least it's a way to show that this is a consistent estimator. And the main difference, if you look at the conditional likelihood, is that you don't have a ratio of two functions. So you don't have like a conditional partition function. And this can be useful in some problems where it's actually not so easy to compute this partition function, even for a discrete model. Okay, so how do you, what's the approach for proving that the final sample version of this estimator behaves well and prove like samples guarantees on the estimation, on the reconstruction? It's a fairly simple method where you just approximate your loss for finite samples with a quadratic loss. And you say, okay, I have a certain loss, I have a quadratic loss, and what I want to estimate is like how far the optimal of this finite sample loss is with respect to the true model. And for this, you do this quadratic lower bound. So you expand the exponential around the true nominal part. And instead of computing the distance between the optimum and the true parameters, you just kind of compute a certain radius or level set that contains the actual true model. That gives you a very conservative, but it gives you an error bound on the distance between your estimates and the true model. This is how it's done. So intuitively, if you do a quadratic lower bound, there are only two quantities that are involved. It's the gradient of this empirical loss function at the optimum and the Hessian of this function at the optimum. So the gradient is fairly easy to bound it and understand how it behaves. And the Hessian is the interesting part. This is actually bounded away by this conditional Fisher information matrix. So this is where this conditional non-degeneracy naturally comes back into the problem. And proving that this loss function behaves well when the problem is non-degenerate, that's the easy part. The hard part is actually proving that the model, the problem is non-degenerate in a nice way. So computing this generalized eigenvalue is, I would say, the non-trivial part in this work for different models. I will not show exactly how we did this, how we prove like for different models that rho is well behaved. If you're interested, I will just refer you to the paper. We can discuss about it after the talk. But I will show that we have done it for different models, and indeed for all the models we have studied, they behave well. Like the rho function is independent of the dimension. So in the end, using this technique, we can give like guarantees, finite sample guarantees. I'll probably not parse into all these parameters. The important point is that if you want to reconstruct like a certain subset of parameters within a certain accuracy, in a certain norm, then we can guarantee that you can do it with a number of samples that is logarithmic in the dimension of your problem and in the parameter space size k of your problem. So the parameter space size is like how many basis functions you use. So for Ising model, where you have like pairwise functions, it will be like proportional to p squared. So you, in the end, you will end up with a number of samples that is log of p cube. The computational complexity also scale like with a number of samples times p, so you end up with something that is proportional to p times the number of parameter space. Actually, it's a local parameter space, so it's like it's p in the case of Ising model, and you end up with an algorithm that is scale like p squared, which is believed to be optimal. The other nice part is that the complexity scale, the number of samples and the computational complexity scales only single exponentially with this local max bias gamma, which is the optimal dependence, and not double exponentially. Okay, so this is a table for different models. I mean, I also not go through it. The most important part is to see that for different models, so not only for Ising, but when you have like pairwise functions, binary L-wise model, or general models like with more general alphabets, you can use like different norms than L infinity norms. You can use two norms, L infinity norms. The only thing that will matter is you have to prove for each of these models that they actually behave well. So this kind of generalized eigenvalue for the Fission information matrix, you have to look at what it is in these different problems. But we have kind of a recipe to do it and plug it back into the general theorem to see that indeed for all of these different models, you have a log p dependence, so p is the number of variables, and exponential dependence, single exponential dependence in the bound or bias bound gamma. One important point is that if you take a general binary or general Q-ary model with a clique order that scales with L, the computational complexity, as mentioned by Ancor in his talk, would just scale exponentially with L. And this will be relevant to the second part of the talk. So that's kind of the only problem. If you want to grow a hierarchy of model with increasing complexity of representation power, by just increasing the order, you also increase the computational complexity exponentially. Okay, so this is just a plot to show that it's not just theoretical, it also works in practice. Like we also have implemented these methods to do some practical work in the field of, I mean, we're mostly primarily interested in quantum computing. So we use this in quantum computers. And here we learn the topology of the machine, which are actually represented by physical interaction. So this exponential distribution represents physical interaction. And you can use it to just learn from quantum annealer samples the physical interactions inside your machine. So you see on the top, these are the couplings that we kind of infer from the model. This is sort of the couplings that are actually zero, which is just like statistical noise. And the blue parts are the couplings that are inside the machine, really realized by the machine. And here you can see the topology spanned by this coupling, which corresponds to the quantum annealers that we have here at Los Alamos. Just to show that it's not just like these bounds that are very loose, of course, are not just, the algorithms are not tight with these very loose bounds, but are actually usable in practice. All right, so the second part of the talk is about how to bypass this exponential scaling in the size of the clique when you want to learn certain graphical models, and how to use neural net to bypass this. So if you look at the standard way of building hierarchies with these models, like you would start, for instance, by, if you want to fit a certain model to a distribution, you would start by postulating that, okay, maybe it's an Ising model. So I have an Ising model. I would just write my favorite estimator to learn the Ising model. In this case, this interaction screening loss. And the computational complexity scales like p squared. Okay, great. But maybe this is not a good fit for the model you're studying. So you have to go to higher order, like 3-body, 4-body, and so on and so forth. So you have this L-wise model, where you have to introduce all the monomial that involve like more than L bodies in your representation, and you write your favorite estimators with this parameterization. And the problem is that the computational complexity scales exponentially with the number of monomials, I mean the order of monomials that you add in your presentation. And in practice, this is really, really limiting, because you don't want to go, already order 2 can be computationally strenuous. So you don't want to go to order 3 or 4, is kind of the max that you can do for a reasonable size problem. But sometimes you have probability distribution that really requires to have all possible orders, but it's not necessarily that all parameters will be relevant. Maybe just a few parameters will be relevant. It will be very sparse, but you need to include all of possible basis term in there. So is there a way to do something when you know that your model is kind of sparse, like there are very few parameters, but have like all possible orders inside it. And it can happen, especially in the problem we have, it mostly also comes from quantum physics background, where you have like distributions that are highly symmetrical. You can like permutate all possible variables, which means that very few terms are actually present because only symmetrical terms are present, but it's not necessarily easy to guess them a priori. So growing the hierarchy by increasing the size of monomial is not necessarily the most efficient thing to do. So one way, the thing we tried experimentally is to replace this complicated polynomial by just a neural net. So you see that in the top, the interaction screening loss just involve like one variable, one special variable of which you want to reconstruct a neighborhood, sigma I, and the rest is like the rest of the polynomial is like its relationship with its neighbors. And this is the part that you can actually replace by a neural network. And what's the idea behind it? Is like the neural network is growing a different kind of hierarchy, and hopefully the neural net will grow immediately a piecewise hierarchy, so involving all possible terms, but it's just sparse, or it's growing, the complexity grows in a different way. So this is one of the first experiments that we did on a very small model to illustrate that indeed the neural net contains kind of all possible order, even though it has very few parameters. So very quickly it grows a higher order hierarchy. So here the model is, it's still small, so you have like only 10 variables, and the true underlying distribution contain all orders up to degree 6. And if I remember, degree 3 and 5 were 0. So you have like some parameters with degree 2, some parameters with degree 4, polynomial at degree 4, and some parameters degree 6. And this is what happened. So the red line are actually the coefficient, like the value is sum for all coefficients of a certain order. And this is the red line. And you have on the green line what you would learn with GRIs of order 6, which is very costly to run because it's a computational complexity of p to the 6, but for a model of size 10, it's actually okay. So, and using a million samples. So you see that GRIs kind of, as expected, learns the model very well, like you reproduce the coefficient of the true model perfectly. And the neural net makes certain mistakes. So here the neural net has a width of size 10 and 2 layers. So not a lot of parameters. And of course, it makes like a few mistakes, but it has, if you look here, it has like order 7 and order 8 mistakes, which means that it contains this order in the polynomial. It represents polynomial of this order. And the way we check it is like we took our neural net, and then we also, it was kind of expensive to do. Once it was trained, we kind of expanded the neural net on a certain polynomial basis to recover the different coefficients of the neural net on this polynomial basis, to see that indeed coefficients all the way to order 8 or 9 were non-zero. So this is just to say that this neural net GRI is kind of a different hierarchy, grows in a different way, and represents higher order interactions very quickly. The second experiment is to see how it behaves for larger problems, not small problems. Like, is it, because before it was like a small problem, so maybe with this number of parameters, it will grow quickly and represent the distribution too quickly. So on the larger problems, and here you have a problem of size 15, it's still like the largest click size is 6. And you have a monomial basis that contains, so if you would do GRIs fully, all the way to order 3 or 4, it contains like 3,000 terms. So it becomes quite intractable. This is what you would need to do GRIs fully and reconstruct the model exactly. So here on the plot, you see the number of training samples on the x-axis and the total variation difference in the learned distribution on the y-axis. And what you see on the purple line is what you would expect the sampling of the error to decrease. It's just 1/² of n. And this is how GRIs perform. So this is GRIs of order 3. So you see that very quickly it flattens, which means like the model is limited. Like you can just add as many samples as you want, the error will just flatten. And here GRIs of order 4, so of course perform better than GRIs of order 3, but it also flattens pretty quickly. And the interesting part is that the neural net is kind of similar, like 2 layers width of size 12 with 10 to the 6 samples. You see that it decreases and go beyond like what you have with GRIs with more parameters. Because you introduce these higher order terms, they're kind of present from the beginning. You can actually have a much lower total variation distance. It seems to start saturating after 10 to the 6, so you need to just increase the number of nodes of width or layers if you want to go to a lower error. But already here, you see that with less parameters, you can obtain something better to learn higher order click size problems. Because it has like already it's included in the neural net representation, you have like higher order polynomials. So yeah, this is just to mention that order 4 is kind of what is practically feasible for GRIs, even for these small problems. And here, the number of parameters, if you just count the number of weights in the neural net, it's like 350, something like this. And GRIs of order 4, it's already like 470. So you have clearly more free parameters in the GRIs problem. And it uses less sample to have a better TB. So how does it work? To do structural learning with GRIs. So this was showing how to represent the distribution. So it's more like parameter learning, where you want to learn the distribution to use it for doing inference later on. And there is actually a way, we found a way to also do structural learning with GRIs. So you may think about having a neural net being like a terrible black box, where it doesn't necessarily tell you something about the structure of the problem. But there is actually a way, a very interesting way to learn the structure with it. So this is the neural net GRIs representation that I showed before. And now I'll do a slight modification. I'll just add a penalty, an L1 penalty, on the neural net weights, and only on the first layer of the neural net weights. This will enforce sparsity in the weights in the first layer of the neural nets. And as a result, if the connections with nodes that are not present, that are not true neighbors of a certain variable, these connections are non-necessary, they will not be favored, and you'll tend to just set the weights to 0 in the first layer if the current node is not connected to, involving two nodes that are non-neighbors. So this is what you see while training the neural net over a certain number of epochs, here 50 epochs, using the same number of samples. This is how the weights will behave in this cost function with a regularizer. So for the weights that involve neighbors in the first layer, the weights will become non-zero, and the weights that involve non-neighbors will actually be set to 0. And this is because they're not needed in the conditional representation. So it's kind of expected, but it was not guaranteed. It's kind of not, but it's kind of expected that they will just decrease to 0 because they can. And by just adding this slight penalty, you can actually just look at the weight of your neural nets, and you can declare that if the weights are 0 or close to 0, they are known neighbors, and if the weights are non-zero, they are neighbors. And this actually is empirically a good estimator for the structure. So yes, you can also do structure recovery with neural nets by putting them in the exponential. So in summary, what I showed is one method to learn a discrete graphical model efficiently, this GRIs method. And you can adapt, you can adapt this method with other type of hierarchies if you want. And here, what we tried empirically is to implement neural net hierarchies for kind of bypass this problem of complexity of computation when the click size is large, And you can do not only parameter learning, distribution learning, but you can actually do structural learning with it by adding a proper regularization. And here are different articles available where we have presented this work. So thanks a lot, and I'm ready to take questions.
All right, virtual applause. So, are there any questions for Mark? Please unmute yourself and feel free to ask. Maybe to start the discussion, let me ask you, so what are the perspectives on extending this methodology to continuous variables?
Yeah, so
thoughts on this?
Yeah, well, I guess if you ask the question, you already know the answer. So there is okay. So there is one body of work where this has been extended to continuous but bounded variable, and there is not much that has been done for continuous unbounded variable. So what are the problems that you have for continuous variables? So I mentioned before that if you use like maybe one of the first loss that comes into your mind is conditional likelihood. Because global likelihood is non-tractable, so conditional likelihood is natural, and we know now that it works for discrete variables. So with conditional likelihood, you again have this partition function problem. It's not necessarily intractable, but you have to compute it. So it may require an integral, a complicated way, or you cannot necessarily have a closed form solution for it, even in continuous and bounded setting. So there is one body of work by Abin Shah and Devavat Shah, and I forgot the last author, that was released on arXiv this spring, where they extended this method, gRise, for continuous bounded variable, because there is no need for computing a partition function. And they show that you can probably actually reconstruct the model when it's bounded and continuous. It's kind of a very natural extension of this work. Now for unbounded variable, it's a bit more subtle, because you either have an issue with conditional likelihood, where you have to compute this partition function, and it requires a complicated integral to compute. Or if you use gRise, then there is another problem, is that since it's an exponential loss, you have a moment problem. Like moments can be unbounded. So that this problem does not arise when it's finite bounded supports continuous variable, but you will have it when the support is unbounded. So these are kind of the state of affair right now for continuous variables. I don't know if it answers the question.
Yeah, thank you. Are there any other questions? So if not, let's move to the discussion room and continue talking over there.